Welcome welcome all to this lecture, our first lecture of sensors and sensor systems. This is a very exciting course in that supposed to equip you with the skills and knowledge on how sensors and sensor systems function, and how to design a sensor system. And by the end of this course, the expectation is that you should be very knowledgeable and you should have acquired adequate skills to design a sensor system. We will not be using the term sensor systems per se. I prefer to use a measurement system. It's more or less the same thing. And so our course outline comprises of 6 main topics that we are going to be looking at throughout the course of this semester. We'll start by discussing the general structure of measurement system, or if you wish, general structure of a sensor system. Then we'll look at static characteristics of the measurement system. Topic number 3 will be the sensing elements. Topic number 4 will be signal conditioning elements. The 5th topic we shall be looking at is the signal processing elements. And the 6th and the final topic in this course will be signal presentation and transmission elements. Now, before I proceed, I need to give some instructions on how we will be proceeding with this course. Let me say that my teaching style is always defined, is always like this. We usually will be having the lectures like this one we are having today, and then we will be having some assignments, theoretical assignments to solve, and we will also be having practicals in this course, so you are not done with doing practicals so far. So we will have a number of practicals, and we will also have a course project. So this unit, in this unit, you will also do a project besides the assignments. And of course, you will do the main exam. And there is the sitting card. Let me say something about the project. Now, you know, a project to me is some work that I assign students that is geared towards solving a real life problem through or by application of the knowledge that is run in this course. And that's how I usually teach my courses. There will always be a project because we expect at the end of the day, this course is supposed to help you solve some problems out there which are meaningful, not just equations and theoretical abstract knowledge. It's supposed to be an opportunity to learn how to solve a real world problem from the knowledge you learn. In the project that I intend to give each one of you, and each one of you will be doing a different project from the other. I understand this class has got only 2 students, and that's a good thing to the teacher because we'll have enough time to offer to each one of you enough supervision. So that's a very good thing in terms of the numbers. My plan is to give you a project where you are expected to use the knowledge you learn in this course to design an experimental trainer module for undergraduate students. This course is very related to a course we teach undergraduate students called electronic instrumentation systems. And in that unit, we have always had a problem because we don't have enough experiments to give to students. We don't have enough trainer modules, especially at their level. And so in this course, your project will be to design a project which will be actually a student trainer module, which is having a sensor and the electronics involved with that sensor, and it should be such that the student can be able to and determine the properties of this system. So if it comes to some measurements a student has to take, then your design should be such that it enables a student to easily take measurements, various measurements, and you should also develop practical manual, student practical manual that the student can use to perform the experiment using your trainer module. So I hope that is understood. The project, about the project that you are going to implement. Something else to say before we start is the assignments also, the theoretical assignments also I will be giving after each lesson, and the way I intend to pursue that area is we will be setting the due dates for submission of assignments, and when you submit your assignment, you will also defend it, meaning you give your assignment, then go to the board and present your work. Explain to me what the solutions to the questions on the assignments are, how you solved the problems. So I will be assessing your solutions, and if I am convinced you got it right, I want you marks. If I am not convinced, then I give you another chance to go and work on your assignment, and this will be the final chance. So it's a very fair approach, because you don't lose marks the first time. And let me say that this is the most important part of the course assessment, not even the final exam, because once you are able to do your assignments well, obviously you will do the exam well. So you take this very seriously. That being said, I think I don't expect any one of you to get anything short of an A. Why? Because by the time we are done with the course, you almost have all the answers to the questions in the exam. So you should be able to have a very easy time sitting for that exam. So that's saying we start the course. Now, I'll be using one reference book titled Principles of Measurement System by John P. Battery. It's a very nice text, and I will be sharing the book with you using WhatsApp. And now to the first topic, which is basically trying to understand what is a measurement system, or what is this we are calling sensor systems and sensors. So we are going to define a few terms so that we are able to understand what the sensor system is eventually. So for purposes of this discussion, let's define some keywords. One is the process. What are we referring to as a process? Let's say, for purposes of this discussion, a process is a system which generates information. And we can give examples. Think of a process as being a chemical reactor, or even an aeroplane, or even gas container where gas reactions are taking place, or even a car, or even your body, be your art, or even a weather system. So let's call those phenomena as a process. Okay, and our job or our objective is to measure or to determine what is going on inside those processes. Okay. So let's also define another term, information, or let's call it information variable. So we then refer to information variable as the product or as the information that is generated by the process. It could be in our chemical plant or in our chemical reactor. There is temperature there. It could be we want to find out what is the pressure inside that reactor. It could be we want to determine the concentration of the chemicals taking place, the chemicals that are being reacted and produced. Or it could be our process is a vehicle, and so we want to know how far it has traveled, the displacement, or the speed at which it is moving, the velocity or the acceleration. So those, we call them information variables. And why variables is because they can change. They keep on changing with time. So they are variables. We know variables are entities which have the flexibility to change. Okay, so then let us also define one more term, the observer. And let us say the observer is a person who needs the information or who needs to access the information from the process. That is, for example, you as a driver needs to know how fast is this vehicle moving, or you as the plant operator needs to know what temperature is the reactor at any given point. Or you as the nurse needs to know what is the heart rate of your patient. So, okay, now you can see we have a process and you have an observer, and the observer needs to know some information from the process. It turns out in most cases, you can't directly interact with the process as the observer. If you need to know the temperature of your reactor, you cannot just look at it and say, oh, the temperature here is 200 degrees Celsius. You cannot smell at your concoction that is being reacted and say, this is the concentration of the molecules inside there. Turns out you need a device to help you determine the information you want. And that device is what we are calling a measurement system. And that is what is being depicted by that figure down there. In that figure, we can see there is a process, and the other side there is an observer. And in between, we have a measurement system. So the observer, the objective or the purpose of the measurement system is to link the observer to the process and provide the observer with the information he needs to know about the process. That's the whole aim and objective of a measurement system. And so we can also say that's the whole business of a sensor system. It's supposed to interact with the process and give the observer the information he wants. And that's all about our course. Developing a system that will interact with the process, whichever process it is, probe the information the observer needs, and relay that information to the observer in a manner that the observer can understand. That's the whole business of the measurement system or a sensor system. We can say something about this measurement system. You see, the process provides us with the input to the measurement system. The process gives the input, produces the input to the measurement system. And this input is actually the true value of the variable being measured. It's actually what we are looking for, is the true value of the information that we are looking for. And then the measurement system takes that input, does some processing so that it can conform it to a form that the observer can understand, and then gives an output. And this output is what we call the measured value of the variable. It's the measured value of the variable. And the question which might be asked is the input from the process always equal to what the measuring system gives us an output? Ideally, that should be the case. The input value should be equal to the output value or measured value in an ideal situation. But often, that is not always the case. The measured value will have some error, and deviation from the true value. So basically, this is what I've trying to explain, that we can now refer to the information variable as measured value. The input to the measurement system is the true value of the variable. The system output is the measured value of the variable. Sorry. The input to the measurement system is the true value of the variable, and the output is the measured value. And we are saying ideally the measured value would be equal to the true value. The accuracy of the system can be defined as the closeness of the measured value to the true value. That's how we define accuracy, the closeness of the measured value to the true value. A perfectly accurate system is a theoretical ideal, and the accuracy of a real system is identified using the measurement system error, where the error is the difference between the value, the measured value, and the true value. Or put differently, the error is the system output minus the system input. This is something we know. It's not very difficult. Okay, so having introduced those concepts, let's look at the structure of a measuring system. Turns out that a measuring system contains several blocks or several elements, if you wish. And it's possible to identify 4 types of blocks in a measurement system. And this diagram here shows the 4 blocks. We start with the variable or the parameter that we are interested in measuring, the input. Could be temperature, it could be pressure, it could be anything. Then what probes that parameter is an element that we are calling the sensing element. It takes the physical entity and converts it into an electrical signal. Then that signal is taken to another block or another element that we are calling signal conditioning element. And the signal conditioning element does this. It transforms the input from the sensing element to a form which is more suitable for further processing. And we are going to say more about that shortly. Then the signal from the signal conditioning element is taken to another block that we call signal processing element. And what does this block does? It transforms the output from the signal conditioning element into a form which is more suitable for data presentation element or for subsequent processing. Then finally, we find we have data presentation element. This takes its input from signal processing element and conveys that value to the observer, gives an output. Okay, so let's say something briefly about the sensing element. Actually, let's say something briefly about each of those elements. I'll start with the sensing element. The sensing element is usually in contact with the process that is being measured, and it gives an output that somehow depends with the variable or the information being measured. So the output of the sensing element is somehow related to the variable that is being measured, the parameter that is being measured. The relationship between the output of the sensing element and the input, that is the parameter of interest, may be linear in some cases, it may be non-linear in some cases, and we are going to come across all those different types of sensors which are either linear or non-linear. But to give some examples of sensing elements, we have an example being a device that is used to measure temperature that we call thermocouple. A thermocouple takes thermodynamic temperature or heat and gives us its output an electrical signal in form of voltage in the millivoltage signal that is somehow dependent on the temperature being probed. We are going to discuss somewhat how the thermocouple works, but I would request you, I would actually recommend that you watch this YouTube video that explains what a thermocouple is. Another example of a sensing element is a strain gauge, where the resistance depends on the mechanical strain. Strain gauge is used in measurement systems that measure weight, sometimes strain, and so it's a very widely used sensing element. And again, I have included a YouTube video that you must watch to understand the working principle and the construction of a strain gauge. We have another device used to measure flow rate of liquid. We call it orifice plate. Again, watch the given video to understand how an orifice plate measures flow rate. It actually converts flow rate into pressure difference. Now, you could have a measurement system that has got more than one sensing element. In that case, the sensing element that is directly in contact with the process being measured, we refer to it as the primary sensing element. And the other sensing elements that follow, we refer to them as the secondary sensing elements. Next, we go to signal conditioning elements. We said they take the output of the sensing element and convert that output into a form more suitable for further processing. Usually, it is a DC voltage or DC current or a frequency signal. And some examples of signal conditioning elements include the diffraction bridge or what we call Wheatstone bridge. And the Wheatstone bridge converts impedance change to voltage change. I am sure you have come across a diffraction bridge previously, but we are going to discuss it because it's an element that is very widely used, and it is necessary that you understand fully how it works. Number two example of a signal conditioning element is a signal amplifier. For example, you have a thermocouple which generates a millivolt signal in response to a temperature measurement. Millivolt signal is very weak, so before you take it to other elements for further processing, you need to amplify that signal. So an amplifier comes in as a signal conditioning element. Another example is an oscillator. An oscillator is a device that converts impedance change into a variable frequency voltage. And we are going to discuss this in some detail in future. So the diagrams show a schematic diagrams of diffraction bridges. Diffraction bridge is made of a network of 4 resistive devices. Generally speaking, diffraction bridge is made of a network of 4 impedance elements. You know, impedance is the general term used to describe resistance to flow of current. In case of an ohmic conductors, we talk of resistance. In case of things like capacitors, resistance often to current due to elements like capacitors and inductors, we talk of reactances. In general, resistance and reactances are referred to as impedance. So you could have a Wheatstone bridge made of resistors. You could have a Wheatstone bridge made of capacitors. You could have a Wheatstone bridge made of inductors. And it turns out that the output from a Wheatstone bridge is now taken for further processing. And in the first diagram, you can see there is an op-amp for amplifying that signal. Now, in the second diagram, we have now a resistive Wheatstone bridge where you have 3 fixed resistors, and the 4th resistor is our sensor, which is actually what? A strain gauge. That's a strain gauge. And we connect it the way it is shown, and the output is obtained at point C and D and taken to subsequent measurement system element, that is a signal processing block. So next we discuss the signal processing element. And here you have the signal from the signal conditioning element being converted into a form that is suitable for presentation to the observer. And then examples include an analog to digital converter, which converts a voltage signal into digital form for input to a computer, or a computer itself, which does computation of the measured signal and present it to the display system. And finally, we look at data presentation element. This presents the measured value in form that can be easily recognized by the observer. And the examples of data presentation elements include a pointer or a scale indicator, chart recorder, alphanumerical display, visual display unit, anything that presents the information to the observer falls under this category. And let me be quick to say that you could also have another stage besides presentation. It could be we want to transmit that information to a distant place where the observer is. So then we could have a data transmission element. Or it could be that we want to store the measured data. So we could have data storage elements. So much as we are saying that's a block diagram of a measurement system, it could be in diverse. We could also have data transmission elements, and we could also have data storage elements in that block diagram as well. So we have some diagrams that gives examples of a measurement system. And the first diagram is a diagram of a temperature measurement system, where the sensing element is a thermocouple, which receives temperature and gives an output, which is a millivolt signal. And then it goes to the signal conditioning element. There are two signal conditioning elements here. There is the autoreference junction compensation, and we are going to say more about that, but know that is a signal condition, is an example of a signal conditioning element. Then we take the signal to the amplifier. Then at the signal processing elements, we have analog to digital converter, which converts the analog signal from the amplifier to a digital signal and takes it to the computer for more computation, for more for further computation. And after the final computation is done, it's relayed to the data presentation, which is a vision display unit, and then the observer can observe the temperature. The second diagram shows an example of speed measuring system, a vehicle speed measurement system, where your sensing element is a tacon generator. A tacon generator is able to take the rotations of the wheel of the vehicle or the engine and convert those rotations to electrical signals, electrical pulses. And the electrical pulses are taken to the signal conditioning system, in this case, a device called, or an element, an electronic system called schemate trigger, which takes the input and converts it into voltage pulses. The tachometer gives its outputs as sinusoidal signal, and the schemate trigger gives its output as pulses, electrical pulses, which are taken to the counter, digital counter, to determine the speed. The counter now generates a digital number which represents the speed, and that number is taken to the computer for further processing and then displayed. Then the third example is an example of flow rate sensor, liquid flow rate sensor, where your primary sensing element is the orifice plate. I send you watch a video of how our orifice plate works. It receives the true flow rate and it gives differential pressure. And then we have the sensing plus signal conditioning element being differential pressure transmitter. This one converts the pressure into an electrical signal and transmits that electrical signal to analog to digital converter, which gives a digital number and presents it to the computer for further processing. And then the flow rate is recorded, is displayed by the chart recorder. And the last example shown there is an example of weight measurement system where you have the cantilever. This is the sensor which converts the weight into strain. So it takes weight, converts it into strain. Then we have a strain gauge as the secondary sensor, which takes the strain from the cantilever and converts it into a resistance parameter variable. And from there, we have a diffraction bridge, which converts resistance measurement to a voltage signal in a millivolt range. Then, as a signal conditioning still, you have an amplifier which boosts the signal to a voltage range. Then you take it to analog to digital converter to convert that signal to a digital number, which is then presented to a computer for further computation and then displayed by a digital display. So now you can see how a measurement system indeed has got different blocks or stages, and each stage has got a role that it plays. And so if you are presented with sensor system or a measuring system, as a instrumentation person, you need to ask yourself, can I identify these blocks in this system? Can I identify which is the sensor, which is the signal conditioning element, which are the signal processing elements, which are the data presentation element? And once you are able to do that, then you understand the system well. And in case it breaks down, you can be able to do troubleshooting. Now, these are where these blocks or these elements coupled to other blocks. Sometimes you could have a signal from a given block being multiplied by a signal from another block, or it could be two signals are being added or subtracted like that. And each operation is denoted by some symbols. So it's important to understand the notations used to represent whichever operation the signals might be undergoing. And for purposes of this course, we are going to represent our signals graphically as follows. If we have two signals that are being summed, then this symbol, the first symbol, represents that operation. We are taking a variable x and we are taking variable y and adding them to get an output signal Z. The second symbol represents two signals being subtracted. The third one represents a signal being multiplied by a constant k to get an output y. The fourth symbol represents two variables or two signals that are being multiplied to get an output signal, which is the product of the two signals. Then we come down here and we find a signal X, which is supposed to undergo some mathematical operation. So the operation is represented by a function symbol, a mathematical function symbol. And that function can be anything. It should be defined. It could be any mathematical operation. Next, we have a symbol representing how a signal can be integrated. And lastly, we have a symbol representing a signal undergoing differentiation. Okay. So those symbols are used to show or to represent block diagrams showing how signals are manipulated by a system. And we are going to see them being used a lot in our course. So in conclusion, we have tried to describe what a measurement system is. Along the way, we have discussed that the output given by a measuring system is not usually the true input measure coming from the process, but has got errors. And the most important thing is to understand the error of a measurement system. We have also shown that a measuring system contains a number of blocks or a number of elements, and these are sensing elements, signal conditioning elements, signal processing elements, data presentation elements, and we have given examples of measuring systems that perform different functions. So that's what we have covered in this lesson. And before I wind up, I told you I will be giving assignments. So I have given 3 assignments. These assignments, I think we should be able to do them. They are simple assignments. They will refresh your knowledge on a few concepts that you must have learned previously. And we should be presenting this assignment next week. So please spend your time to work on the assignment and let me know when you are ready to submit and defend your assignment. So thank you very much for listening.